In this lesson, we'll be talking about transformations of functions. Transformations of functions builds on a catalog of different types of functions that we can discuss. What can we do with the individual functions that we now understand to make them a little bit more versatile? So that's where transformation comes in. To do a transformation, we first need to understand the different types of transformations and what they all look like. There's a little bit of data to pick up at the beginning, and there's a lot of detail to it, but you'll do enough examples that once it's all finished, you'll be able to see what you're doing and can do it quickly. A transformation can be either a shift, a reflection, or a stretch, or some combination of these. So we'll start off by talking about the shifting. So first off, a horizontal shift. A horizontal shift will look in this form. You've got some function, and inside the function you either have an x minus h or an x plus h in terms of the graph. X minus some number, x plus some number, and whatever the original function was where the x was, that gets changed to x minus h or x plus h. Here's our first example. We've got the absolute value of x, the absolute value of x minus 2, and the absolute value of x plus 3. Let's just graph the absolute value of x first, and we know this to be that graph that looks like a V. And then we've got the graph y equals the absolute value of x minus 2. Now it says x minus 2, which if we look up here in our definition, if it says x minus h, that means we're going to move h units to the right. So it's reversed here. Minus 2 means move to the right 2. And here's what my graph looks like whenever I do that. Next is y equals the absolute value of x plus 3. And so I can move to the left 3 because of the plus. Again, it's all reversed. X plus 3 means take this graph and move it to the left 3. Just a few more examples of what this could look like. Say x plus 5 squared. Notice that the x plus 5 is in the parentheses. Absolute value of x minus 4. Again, x minus 4 is inside the absolute value. X plus 2 cubed. Again, the x plus 2 is inside the parentheses. So when it's inside the function, it's a horizontal shift. Vertical shift looks like you've done something on the outside of the function. You've either got the actual function plus a value or the actual function minus a value. When this happens, we go exactly the way that we would expect. Plus k means go up k, up 2, or up 5, or whatever k may be. If it's a minus k, we go downward. Nothing is reversed when it's on the outside. The vertical shift is on the outside, and it goes exactly the way we would expect. Let's graph y equals x squared. We've done this graph, but it's also in our catalog. X squared plus 2 means, again, since it's on the outside, we go up 2. X squared minus 3 means that we would start from the original graph and go down 3. The vertical shift is on the outside, and it goes exactly where you would expect it to with the plus and the minus. Some additional examples of vertical shifts are y equals x squared plus 5. The 5 is on the outside of the x squared. Absolute value of x minus 4. The minus 4 is on the outside of the absolute value. X cubed plus 2. The plus 2 is on the outside of the x cubed. And so these are our vertical shifts. Next is the idea of a reflection. We can reflect two different ways. We can do the negative of the original function, which reflects across the x-axis. So if you start above, you flip down to below. If you start below, you flip up to above. Negative f of x is a reflection across the x-axis. You might think of it as a reflection of the y-coordinates. Since it's on the outside and it does things with the y-coordinates, maybe that makes sense. Next is the graph of f of negative x. Negative x meaning that when you actually have where x was, the inside of the function is negative x. Not a negative in front of the whole thing, but the inside the parentheses, inside the absolute value is negative x. When we run across that, we flip across the y-axis. So if something starts positive, it moves across the y-axis to the negative. If it starts negative, it moves across the y-axis to get to the positive. That is how we set up a reflection when the negative is on the inside. Let's take a look at an example of this. The first graph is y equals the square root of x. Now y equals the square root of x, we already know this from our catalog of functions. We know that it looks something like this. And so what the reflections are going to do is change the direction in which it's going. Y equals the negative square root of x. Remember, when the negative is on the outside, that changes the y values to the other side. And this is a reflection across the x-axis. So y equals the negative square root of x will look something like this. And then finally we've got y equals the square root of negative x. This time the negative is on the inside. So we're expecting this to be a reflection of the x-coordinates. Or you could think of it as a reflection across the y-axis. So that will look something like this. Getting closer to finished, the vertical shrinking and stretching. Vertical shrinking and stretching is when you've got some number on, again, the outside of the graph. And that number, depending on whether it's greater than 1 or less than 1, is what helps us see what's going on with the function. If you multiply the outside of the function by a greater than 1, then you grow. It stretches. And if you multiply by something less than 1, it compresses the graph, or shrinks the graph, if you will. Y equals x cubed, let's just draw that graph. So if I were to do y equals 2x cubed, that stretches the graph by a factor of 2. And what it really does is stretches the y coordinates. So I'm kind of looking at this 1 right here, and I'm going to move it up to 2 in the process of doing this. And also the negative 2. So this graph is a little bit narrower. It's been stretched out vertically. And then finally, y equals 1/2 x cubed. I'll use a similar guideline for my work here. And we see that this graph is a little bit wider, a little bit shorter than the original one. We're ready to put all this together. The first thing we do when we have to use multiple transformations at the same time, we do horizontal shifting first. Then we do vertical shifting last, and everything else in between. The rest of the order actually does not matter. Horizontal shifting first, vertical shifting last. So we can think of HEV as an acronym, like Henry eats vegetables, or Henry enjoys vegetables, or some other acronym that you can think of, but the idea is HEV. Horizontal shifting, everything else, vertical shifting. So what we're going to do here is start out by deciding what is the original function, the parent function, if you will, of this equation. The negative is a transformation. It's the one that flips it. The +1 is a shift, and the +2 is a shift. What we're left with is that the parent function is just the y equals x cubed. So you look for the transformations and you say that's not part of the original function. That's not part of the original function. And eventually you run into, well, what makes up the essence of the function? What function is being transformed here? And it turns out to be y equals x cubed. So let's draw it. The first step is horizontal shifting, which is the +1. So since it's a horizontal shift, remember horizontal shifting is reversed. So when I see +1, I'm going to move to the left 1. Next step is the everything else step. So whatever is not a vertical shift, I'll do now, which is just the minus. The minus on the outside means I flip my y coordinates. I flip across the x-axis. Last is the vertical shifting. The +2 is on the outside of the function, so that's a vertical shift, and we'll do it exactly the way that it looks. +2 means move up 2. This is our final answer. It would not be a bad idea to stop and try these yourself before I do each one. Even if it's not a star problem, it wouldn't hurt to try it because these will take some practice. We've got the cube root of -x - 1 + 3. The negative x is a transformation. The minus 1 is a transformation. The plus 3 is a transformation. So what we're left with is y equals the cube root of x. So just remove in your head all the transformations and see what's left. So the cube root of x, if you recall, looks something like this. And now let's do our transformations. Horizontal shifting is first. Minus 1 means move to the right one. It's on the inside. So it does the opposite. And that's our first transformation. The next one is the negative sign. The negative sign means flip across the y-axis. Reflect all of your x-coordinates. Now you need to be careful about where you're reflecting. We're reflecting across the y-axis. What it's going to look like is something like this. Now if you aren't careful, you might put this turning point over at 1, but you're reflecting across the y-axis, which means it flips all the way over here. Finally, the plus 3. The vertical shifting is last. It's not part of the everything else category, and that simply says to go up 3. The 3 is a transformation. It's a stretch. The minus 2 is a horizontal shift. The minus 1 is a vertical shift. And so what I'm left with as my parent function is just the absolute value of x. Horizontal shifting first is the minus 2. Again, because it's on the inside, we're going to do the opposite. It's going to go right 2. Next is the everything else category, everything but the vertical shifting. That's the 3 on the outside. And so what that's going to do is it's going to stretch my graph by a factor of 3. One way to think about this is multiply all your y coordinates by 3. So we've got this point 2, 0. The y coordinate is still 2, 0. The point 3, 1, when I multiply my y coordinate by 3, I get 3, 3. 1, 1 similarly becomes 1, 3. And you could do more, but as you can see, this graph is now a good bit narrower than it was before since we stretched it vertically. Then one final step is the minus 1, which is a vertical shift. So we'll move everything down by 1. I'm just going to plot a couple of these points I had before and draw the graph. So there's your final answer in red. Two more examples. Again, feel free to try these beforehand. Negative 1 over x minus 2 squared plus 1. Now this one is a little bit strange, but I'm going to tell you, and then I'll try to explain it, is that 1 over x squared is going to be the original parent function. And here's why. The minus 2 is a transformation, and the plus 1 is a transformation. So I see that my inside is this denominator of x squared. With that said, the negative 1 is just a constant multiple, so that's a transformation also. So what it boils down to is all that's left is 1 over x squared. And if we are to draw this graph, the parent function does something like this. It's got an asymptote, and it rises towards 0 in the center and falls towards the x-axis on both sides. The first thing is horizontal shifting, which is again the minus 2. So let's be careful here. When I shift this graph to the right by 2, I had an asymptote at x equals 0 before. Now it is at x equals 2. Then I'll shift everything over. Alright, next is the everything else category. So the plus 1 is a vertical shift. It'll be left until last. But we do have the negative 1. The negative 1 is going to flip the graph across the x-axis, thus flipping the y's. The asymptote doesn't change when I do this. And I just have that the graph is now falling instead of rising that far. One more is the plus 1, and that's going to make it go up 1. So if it was approaching the x-axis before, now it's going to approach the line above the x-axis. Y equals 1. The vertical axis does not change, and then now the graph looks like so. And that's our final answer. Alright, the last one is one that you should even more than the others try first. Now that you've tried it, I hope you have a nice clean answer. The parent function is y equals x squared. The negative 2, the plus 3, and the minus 1 are all transformations. So we'll start with the graph of y equals x squared. And then the plus 3 is a horizontal shift. We're going to move to the left 3 because of it. We've got our horizontal shift. Then we've got this negative 2. The negative 2 is going to flip the graph over because it's negative, and the 2 is going to stretch the graph out. Our y coordinates, if you'd like, are going to get multiplied by 2 but also flipped. That's really the same thing as it just being multiplied by negative 2. These y coordinates were at 1 on both, and so now they're going to be at negative 2. The graph is flipping and stretching. And then finally we've got the minus 1. The minus 1 is a vertical shift, so it shifts all of our points down by 1, and I get the graph looking something like this. That's our final answer.